So we've been talking about collaborative robots in the lab lately quite a bit. And I figured, when Padir reached out and said, why don't you give a 15-minute talk? I said, all right, so let's put the title in and let's try to fill it in with the work that we are doing and what the work that we will be doing in the next year, and then let's see how it looks like. So I am from Northeastern University, as Akshay said. I had the pleasure and misery of working on the DARPA Robotics Challenge. That was my talk, 3 years ago at the summit. And since then, the lab has turned into an experimental lab. What we try to do is not just get one-off results, but we try to really pound on getting results repeatedly and reproducibly, so that we can get robots into practice. And one of the last slides, I'll talk about our new project coming up, and that will hopefully tie the whole thing together. So in the lab, please don't try to read the fine text. We have 3 main lines of research. A 4th one is being added. The first line is on humanoid robots. We've been working, as I said, we've done the DARPA Robotics Challenge. I was at WPI at that point, and we graciously exited the challenge. And then we've been working with NASA on their Valkyrie, humanoid robot Valkyrie, and then that extended upon to a project with Department of Energy. We do have a small but growing line of work on post-disaster, automated post-disaster assessment using aerial systems. We've been working on, it was actually one of the very first projects that we got funded on assistive robots. And then the latest is the advanced robots for manufacturing. So I'll start with, again, the spirit of the talk is on collaborative robots. What do I mean by that? Robots helping humans, humans helping robots, robots working in the same environments with humans. But when I say the same environment, I don't envision the same physical space. For example, in a DOE setting, in a Department of Energy, in a nuclear facility, your humans may be behind the wall, but they're still trying to control the robot. So I claim that as a collaborative robot application. So I'll start with a very brief update on what's going on with NASA's Valkyrie system. Again, I think it was last year or a couple years ago, we talked about this quite a bit. And if you've been following the rolling videos, we were awarded one of the 2 Valkyries that was handed over to research groups in 2015. And then this year was actually the end of the project. So here's an interesting fact, and this is a pitch actually. NASA, when the project ended, NASA consolidated both robots. MIT returned theirs to Johnson Space Center, but we said, look, don't leave Massachusetts without a robot. So we moved our robot to Mass Robotics, which is a small incubator space down in the seaport area. And now it became a shared infrastructure. So there are simulators available. We provide training sessions. So if you are interested in really getting some work done with humanoids, you can get trained on the robot, and you can get algorithms running in simulation, and then you'll have a chance to come and test your algorithms on the robot. Actually, in January, we hosted a workshop where researchers from WPI, Brown, and Tufts came in, and in one day, we can get you started. It's a complex system. The way that I pitch this is that it's the cutting edge mobile manipulator, bipedal mobile manipulator for research purposes. It's not available for practical applications, but for research purposes, that has been designed and built by the NASA's Johnson Space Center. So what did we do with this robot? In my opinion, to achieve through collaboration between humans and robots, a few of the things need to happen. Robots will need to have more and more autonomy. Now, when I start talking about autonomy in my classes, I ask the class, how many of you think that you're autonomous? Now, let me ask the same question. How many of you think that you're autonomous? What's the definition of autonomy, right? So, somebody gave us a schedule to be here today. We go to work and so on and so forth. So the concept of autonomy fits in that slide. And what we've been doing mostly is supervised autonomy, where there is a set of tasks that the robots needs to follow. Maybe Johnson Space Center sends in a set of commands that needs to happen that day, or a set of tasks, and robot tries to execute those at the task level. So our work in the past few years has focused on 3 layers of planning and control in the lab. We created methods in the task execution level. So we became actually with the DRC an optimization-based motion planning and control lab. We do optimization-based inverse kinematics, and then we created motion templates for the robots to be able to capture some of the operator intuition. For those of you who follow the DARPA Robotics Challenge, the concept was, your operator says turn the valve, and then robot turns the valve, right? So, but then sometimes there are those intricacies in those decision making, right? So when you say turn the valve, when the operator says, he or she has an intuition about, am I close enough to the valve? If I reach with the right arm versus the right arm, will I be more successful? How likely that I will fail? So there's a lot of decision making happening at that high level, at the operator level. And then we wanted to develop a framework to enable or to capture some of those intuitive decisions, and what I will talk about next. So this was a recap of, I guess, last year's talk. So what happened this year was we been mostly focusing on nuclear cleanup tasks that are happening in the US. When you talk about nuclear disasters, human, man-made or disaster or natural, of course Fukushima comes to mind. But in the US, there is a huge cleanup effort. Actually, by the same token, there are a lot of cleanup efforts that's ongoing in Europe. This is a 75-year timeline, $250 billion budgets are being estimated, and so on and so forth. So it's major. So this is the Cold War nuclear facilities that needs to be cleaned up, and what happens is they collect everything and then send it into this really state-of-the-art waste processing facility. It turns into glass, but then somebody has to go into these 50-year-old rooms, chambers, where no one has gone in that period of time, and basically collect all the waste, and move things around, collect all the waste, and then so that we can clean it. So this is a Department of Energy funded project, and the idea here was you cannot send in your human to collaborate with your robot next to it, but then human can be behind the wall or at a different facility. Your robot goes in and still does it. I always get the question, why a humanoid form factor? Well, if we design environments for humans to operate, the humanoid form factor really makes the case. And actually, some of the use cases that we are looking at in this nuclear energy applications is that there are very narrow passages. There are very tight areas where these robots will need to operate. So with this, what we did was, this is a recent result. We are primarily looking at these boxes called glove boxes in nuclear facilities. When I say a glove box, you put your arms inside those ports, and there's something dangerous happening inside, and we are trying to manipulate. Now, this is a very interesting problem from a robotics perspective, right? Especially if you're trying to solve an optimization problem. That you have 32 joints that you need to coordinate, and then you do something useful. This is, as I said, these are the beginnings of our work in this area. Can we even autonomously put our hands, and can we tell the robot, go in and start working on, start pushing things around. So what are we doing with this? First of all, what is the concept of manipulability? What is the concept of, your human thinks, yes, robot you can do it, but then can we embody some of those decisions into robots' decision making? What can I do? Where can I reach? So what we did was, in one of our recent papers, is that we are simply looking at these polytops at the end effector of the robot, when the robot's arms are inside those constrained environments, and where can we move? Where can we reach? In another study, we started looking at what happens if the robot is making contact with the ports, right? Rather than trying to avoid contacts, maybe we can make those contacts to leverage, to have better stability, because humanoid robots are prone to falling, right? Falls. And one of the famous videos of the DRC was the falling robots video, obviously. But can we now leverage the contacts in this environment? So what you're seeing is that in those polytopes, when the robot is away from the glove box, yes, it has a lot of manipulability. It can reach in many locations. But then as you start putting the robot's hand in the third one, when the end effector is really in that port environment, your manipulability shrinks. But then once you're inside, you gain a little bit more, right? So once you're inside, you have a little bit more space to play with. So this initiated another line of research, which we weren't really thinking when this project started. And again, in the whole idea of, is this running? Nope. Here we go. So anytime you talk to a safety critical application engineer, a nuclear engineer, they say, well, we got to be risk averse, right? How can you tell me that your system is not going to fail? How can you guarantee? Now, for a 32 degree of freedom system like this, even if you have the best tools, to be able to prove that this system is not going to fail is a hard thing. So what we started doing is we started quantifying risk measures. And what we call this is a risk-informed decision making. The idea is for a humanoid robot, it has two arms. It needs to balance. There needs to be a lot of things. But it can reach with the left arm and pick up the bottle if the task is a simple pick and place. Or you can do it with your right arm. Or you can do handovers, right? So there are infinitely many solutions, basically, to perform these tasks. So what we are looking at is a level of failures, right? A set of failures. What are some of the failures? You can collide with the environment. Some of them are less costly. You can fall, which is catastrophic, right? So can we leverage some of the things that economists already figured out and maybe have a measure? Embed some level of risk information into the robot autonomy. So the idea is that, robot, if it's going to fail, it's still going to fail, but it can report back and say that, if I execute these trajectories, these motions, then I'm 85% likely to achieve the task versus 90% and so on and so forth. So, if you're noticing, what you're seeing is that this is a very simple pick and place task, moving the book from one side of the box to the other, and we are performing different trajectories, different motions, and then we are really messing up with the robot by adding that weight at the arm. That's the simulated uncertainty in the system, and one of the failure modes is obviously falling. I talked about this. So, what we really do is we classify, we generate a taxonomy of failures, and some of them are more severe, so we have a severance factor, and then based on that we can calculate a total risk value. Again, that's not, humans does this, very intuitively, right? So is there one math that captures everything? Absolutely not. We don't claim that we figured everything out yet, but this is a step forward. The next set of slides talks about our work in helping elderly in the home, and this is I'll start it right here. As the students are packing the robots and getting the crates ready to go to Montreal for RoboCup 2018, this is, I know MathWorks is getting involved. This is our qualification video. We are one of the 12 teams qualified around the world to participate in the standard challenge, standard platform challenge. We are using Toyota's HSR, Human Support Robot, and this is, yes, fully autonomous, but there's a lot of collaboration, handover tasks, right? So bring me bottle. So my student says, HSR, go and bring me the bottle. Or there's fully autonomous tasks where the robot sorts groceries that are on the table. So when you look at this, going back to the title, collaborative robots, what are the challenges, what are the opportunities? So there is, our paradigm has been, let's try to look at all the cases, and this has been the theme actually of the summit in the past couple of days. Let's try to figure out all the cases and try to come up with mitigation, or plans. That's not really that effective. So what what you will see, for example, if you watch closely, your sensor system underestimates or miscalculates the size of the bottle. Everything is good, and then as you try to pulling down, your bottle hits the side of the tabletop and so on and so forth. So we have quite a bit of ways to go in there. So I'll just go forward a little bit. This is one of the tasks, and actually we did really well last year in this task. And this is sorting your groceries. You came in home, dropped your bag of goodies, and it's being sorted in the shelves. So last year, in 3 minutes, we were able to do one item. This year, we can do up to 7, 8. And one of the key capabilities that we developed what I call what I call grasping on the fly. So we used to plan, first let's plan the pick, and then let's plan the place, right? So you're basically doing a greedy solution, greedy approach to that planning. But now what the robot does is it plans both pick and place, and then it can do it much more efficiently and faster. And actually, I think students were having fun when they shoot this video. Robot looks the other way around as it's putting the item on. And then they do a lot of fun things. This was one of the packages available. They were trying to classify, who is the neutral person, who is the angry person, and of course, we were all laughing about that. We are headed to Japan for this World Robot Summit in August, Robotics for Happiness. So this will kick off this year, and then it'll continue into 2020. We are expecting that there will be a connection to the Olympics. Now, the connection to MathWorks is that this robot platform is available as a MATLAB in MATLAB simulation, so you can really continue to work on the simulation and get things done in MATLAB. We've been using quite a bit of MATLAB Robotic Systems Toolbox. 3 more slides. This is one thing that we've been pushing quite a lot, right? So you get a new PhD student. If the student doesn't have any robotics background, how do you get them to work, right? So for the past year or so, we've been working with MathWorks. Actually, they funded a small curriculum development grant where we are now developing an open platform for mobile manipulation, well, except for the Turtlebot. But then this becomes, students come with MATLAB background, but students usually don't come with robot operating systems background. So this becomes a bridge between the two. So before I end, I'm 2 minutes late, but before I end, so this is sneak preview for next year. I mentioned that collaborative robots and a new project that we just kicked off last week. And there are no robots in this video. You will see a small fish plant. It turns out United States cannot process the fish that are caught on US waters. So what happens is the fish is frozen on the ships, and they are sent to other places to get processed, and then they are imported back to the country. So we identified this as a critical gap in the US economy. And there is a new organization called Advanced Robotics for Manufacturing Institute in the US. This is 150 organizations that came together with funding from government, industry, and academia. It acts on a membership model. And our project is on taking some of the use cases that we saw in a plant, in a seafood processing plant, and automate those, because they cannot find enough workers. Even if you have workers, the retaining workers is an issue because it's a cold environment, slippery, smelly, and so on. And I have this video, right? It's keep doing. All that woman does is picks up the fillets, grades them by weight, roughly 10 to 12 ounce, 12 to 14 ounce, and sorts them. Sometimes, once in a while, they check the firmness. If it doesn't feel right, it goes into the garbage. And we think that those use cases can be automated. With this, I will thank all of you. The group has a research scientist and a number of PhD students, and we've been funded quite good. Thank you.